So chapter 9 introduced a whole lot of new ideas to you. This will be sort of a fun way to end it up. I'm just going to kind of explore a few different graphs that you can make with some of these polar coordinates. So the first thing I want to look at is r equals 4 sine theta. And to make a graph, just like we typically do with most things, we're going to just do a chart here. We've got some different angles as inputs, kind of like x would be in a normal function. We're going to see what the radius comes out to be as your output, kind of like the y in a normal function. So let's kind of run through and just see what happens. If you plug in pi over 6 for theta, all right, well, sine of pi over 6, that would be a half. 4 times a half would be 2. If you plug in pi over 4, sine of pi over 4 is square root of 2 over 2. Multiplied by 4, so it would be 2 square root of 2. Square root of 2 is about 1.4, so about 2.8. We'll go ahead and just say 2 square root of 2 for now, but it's about, well, let's put it up above here, about 2.8. All right, pi over 3. All right, well, if you're here, that's square root of 3 over 2 for the ratio. So 2 times the square root of 3 if you work it all out. Square root of 3 is about 1.7, so double that's about 3.5 roughly. So about 3.5. All right, pi over 2. Well, sine pi over 2 is 1, so 4 times 1 is 4. And then it's going to just repeat from there because you're going to have the same things you just had. So 2 square root of 3 again, 2 square root of 2 again, and 2 again. And I guess I should go ahead and do one more here. Let's go ahead and see what happens if we get to pi. All right, well, sine of pi is 0, so that's back to 0. I probably should have also put 0 on this side. Sine of 0 is 0, so 4 times 0 would be 0. So let's see what happens when we put these on our polar graph. This graph, for whatever reason, is missing the 45-degree line, so I'll just have to add that in when I get there. So sine of 0 would be 0. Let's put a little dot in the middle. We have pi over 6, which is this line. We're at 2. We get to pi over 4. That's what I'm going to have to add in, kind of split the difference here. That was about 2.4, so right in there. We get to pi over 3. We are at about, go back up and look at that, about 3.5. So about right here. When we make it to pi over 2, we're at 4. And then we just kind of repeat what we just had. That was about 2.5, about 2. And it might be kind of hard to see with just these values. You might need to add more to really see what's going on. But this is making a circle. If you want to verify that in the calculator, make sure you do check out mode. This is really important. You do need to be in radians to make these work. The angles were in radians, the way we graphed it, the way we came up with our points. But if you go with degrees, actually I might just show you degrees in a moment, just let you see how crazy it gets. It's not really going to be what you expect. Make sure we are in polar mode. So down here where I've got function right now, I need to go over to polar, make sure that's set. So that's the two things that really you've got to take care of before you try to graph this. So now y equals will be r equals, and that was 4 sine theta. And again, when I hit the variable button now, it's a theta instead of an x. So that should be pretty good. Now, one more thing. This had a radius of 4, or I take that back, had a radius of 2. The maximum distance was 4, like a diameter of 4. So for the window, this only because I've graphed it by hand and know about what it's going to look like. I just want to make this fit in the window a little better. So for the x minimum, I'm just going to put -4, x maximum put 4, and y minimum, I'm going to say -1, and y max I'm going to say 5. And I'm saying that because I've already graphed this thing. I know it only went a couple out in the x direction either way. I know that it was 0 to 4 as far as the bottom to the top, so this should get it pretty close. And remember, you can always come back and adjust the window if it doesn't fit very nice. So I'm happy with this. Let's hit graph, see what it looks like. And there we go. It is a circle, and it looks pretty close to what I had.
So just like everything else in this chapter, you can access this Desmos on the website. I think it's probably easier to just run through and kind of look at them on here. Whatever I do on here, you can definitely do in the calculator. But I think it's just for demonstrating it, I think it's just nicer. So here's the one we just did. There's this circle. And nothing too spectacular going on there. So let's go on to the next shape. And really for this section, all I care about is that you learn the names of the shapes. You can certainly sit down and generate these things by hand. I'm just going to make the graph and let you look at them. I'm not expecting you to sit down and do these by hand. Really just, I want you to kind of see them, be able to play around with it, see the names. In case you can't encounter them later on, this isn't something you're going to see a tremendous amount in most math. Certainly, maybe if you get in some kind of art or design, you might see some of these patterns. So the next shape to look at is called cardioid, and it sounds kind of like heart. That's really what it's going to look like. It's going to be kind of a heart shape. So it's 4 minus 4 sine theta, and we'll look at some of the details of why it looks the way it does. There it is. It kind of looks like a lily pad too. A lot of people will say that it's more like a lily pad, and I kind of can see that too. But it's sort of got a heart shape. It's called a cardioid. So there's that one. And a really similar thing, just to show you how similar, look at the function here. It's 4 minus 4 sine theta. The limicon, I believe, is the French pronunciation, but limicon is usually what we say. It's pretty similar, except this number right here is a little bit bigger than this number, and that's really the only difference. So if I go to graph that one, it's kind of like a lily pad shape, but then it's got this little loop inside of it too. So same basic shape with an added loop. So just to compare those two, again, they're pretty similar, except that I've got a number here bigger than the number out front. So they're real similar. So here's the pattern: something plus something times sine theta, and it works for cosine as well. It just turns it sideways. So let's try that one and see what happens. So the deal really is, if B is bigger than A, then you get this shape right here. You get this little loop inside. If A is bigger than B, you get the heart shape. You don't have the loop. So I just want to show you how that unfolds as A gets small. So again, I got B set to 5, and I'm just going to leave it there. So as A is smaller than B, that loop gets bigger inside. If it goes negative, they actually switch. At 0, it's a circle, just one circle. They kind of come together. Because that should make sense. If that's gone, that's just the first shape we had, something times sine. So as A gets closer to B, the loop gets smaller. And then when it finally makes it to the same number, that's when you get that cardioid shape. And then anywhere past that, it just stays that cardioid shape. Eventually, it starts to look more circular. It's kind of flat on the bottom. It's never going to be quite a circle. It's kind of like a hyperbola versus a parabola. It's never quite going to make a circle, but it's really close, like a flattened out circle down here, and maybe bulged a little bit on the top part. So there's a difference between those two. The next thing is a rose. Now, this one's really fun. I'm going to play around with it and let you see what you can do with it. A lot of students end up pulling this one up just to play with this one. So there's a rose, and it really just looks like any general flower, so I don't know why it's called a rose. But that's the next one. It says 3 cosine 4 theta. So let's kind of focus on what these pieces do here, these two numbers. So let's make a generic one. All right, right now I've got M, which is the number out front, and it's set to, let's go ahead and just make it 5. So that seems to be affecting the size of the shape, kind of like a radius, and that's really all it's doing. The fun part is the number times theta. All right, now that works like frequency. Remember that from when we did trig. So watch what happens as I crank up theta. All right, 1 wasn't very exciting, just one loop. 2 made 4 loops. 3 makes 3 loops. 4 makes 8 loops. 5 is back to 5. So you get this interesting pattern where the odd numbers tells you how many petals it's going to have. Even numbers, it doubles that. And you can explore with why that's happening with frequency and all that. Really, I just wanted to let you kind of see this and play around with it. So we got 12 petals there, back to 7, and then 16, and back to 9, and then 20. But what's really fun, now what I'm doing here on the slider, I made my step 1. Let's make it a really small increment, 0.01. And come back here to somewhere, let's start somewhere kind of nice, like 1.5. When you get just slightly off, start getting all kinds of fun shapes unfolding. And you can put it in motion on here. That's kind of fun. We can slow it down a little bit so you get to see a lot of shapes. So that's kind of a fun thing you can do. Just start it somewhere. Oops. Now I want to go that way. There we go. Oh, those are fun too. Let's start back at the beginning. Get these spiral shapes happening. So all sorts of fun things you can do. If you ever play with the spirograph, it's kind of the same thing. Those really technically are based off parametric equations, but what you're starting to see probably here is that parametrics can graph everything in this section can be kind of graphed with each other. You can graph conics with parametric equations. You can graph these with parametrics. You can actually graph conics with these as well, but we're not going to get into all that. All right, so the rows is kind of the fun one. Finally, the last thing is the limniscate, and that's kind of set off because it's r squared. Now, when I go to graph that, and the same thing's going to happen in your calculator, it doesn't like r squared. All right, your calculator is not going to like that either. If you pull up your calculator, it's going to have just r. Okay, so it doesn't have a place to put r squared. So you have to take the square root, and that's what I did over here. I went ahead and took the square root. And not as fun as the rows. It just kind of makes an infinity looking symbol kind of turned around. And the number in here with the frequency changes the number of loops you have if you want to mess around with that. Whatever you put in there is what you get with these, though. So that's kind of how that plays out. And this number is going to affect the radius, basically. So the bigger you make that number. So that was pretty similar to the rows. It's just generally, it looks kind of like an infinity symbol, but pretty similar. A lot of things that are going on is the same. So that's pretty much all I want to do with you. Just get familiar with some of the names here, play around. It's just supposed to be kind of a fun section to wrap it up.